Hi, I'm Rohan Bull, and this is my Lab 5 Faraday's Law presentation. So, the purpose of this lab is to test the results of a magnetic field slowing down the fall of a magnet, and to be able to explain these observations through Faraday's Law. So, the physics concepts covered in this lab are flux, or the magnetic field passing through, and normal to an area. Faraday's law, the voltage for the derivative of flux with respect to time, and Lenz's law, which states that induced electric current opposite to the change in flux. So in this lab, we are supposed to drop a bar magnet through a tube of aluminum foil. The tube is supposed to represent a sort of solenoid, and the flux is going downwards. So the magnetic force is going upwards, as stated by Lenz's law. And for this lab, we are supposed to find the magnetic force. So here are the procedures. First, we have to note down the measurements of the aluminum foil tube, such as the width of it, the radius, the length, etc. Drop the magnet. Then second, we drop the magnet down the aluminum foil tube, and we record how much time it takes to reach the bottom. We do 5 trials and then take the average of the trials. And why can't we use another tube? Well, we can't use a tube made of ferrous metals because they would end up interfering with Faraday's law. So here's some of the results. The initial measurements of the lab are uh, length of the tube 0.3 meters, radius 0.03 meters, the width of the aluminum foil tube is a 0.005 meters. The mass of the magnet is 0.023 kilograms. And the mu is 2.1 am squared calculated from lab 3. So from my observations, I found the average time to be 0.76 seconds, and from the glow script experiment, 0.33 seconds. Quite a discrepancy. So here's some of the coding. So this is the initial part where we are initializing the tube, as you can see from length 3 with 0.005, inner radius 0.025, and those two add up to the total radius. The initialization of the tube for the extrusion circles, and the initialization of the magnet with the mass, the mu magnitude, and the actual visualization of it. Here's some more coding, which sets a couple more initial conditions, such as the bar magnet's initial spot, followed by how to actually calculate Faraday's law from this glow script. As you can see, there's the t plus delta t, the time change. We have an if statement to determine whether the bar magnet has entered the tube or not. Gravity vector, the magnitude of F, and for ring and tube, it's to and then we have all the flux calculations here. So here is a graph for the velocity versus time of the glow script simulation. As you can see, it steadily increases in meters per second. And on the bottom right is just an image of the final state of the glow script code. The reflection questions. What if the resistivity of the conductor were reduced as close as possible to zero? And how would that change the dynamics of the falling magnet? Well, the magnetic force would grow and the magnet would fall even slower. And what if holes of slots were cut into the tube, and how would this affect the ring current in your model? Well, it would result in a weaker magnetic force since it wouldn't be a perfect cylinder, and there would be magnetic field going through the holes as well, and it would just make it all wonky. The magnetic field would end up falling. Sorry, the bar magnet would end up falling closer to a normal speed rather than the slowed down version.